Question 7. Sulfur trioxide decomposes on heating to form an equilibrium mixture containing sulfur dioxide and oxygen. A sample of sulfur trioxide was heated and allowed to reach equilibrium at a given temperature. The equilibrium mixture contains 6.08 grams of sulfur dioxide. Calculate mass of oxygen in the equilibrium mixture. So, first things first, what we don't do is, there's 6.08 grams of sulfur dioxide, so we just divide by 2. We get the oxygen. You seriously think they would do that for 2 marks? And they wouldn't. First thing we're going to do is, we usually do this for equilibrium moles, not masses. So let's find the moles. Let's find the moles of SO2. Well, it's going to be mass 6.08 over mR, and the mR is going to be 64.1. Once we do that in the calculator, we will get 0.0949 moles. Now we've got the moles of SO2, we can find out the moles of O2. The moles of O2 is just going to be that divided by 2. So moles of O2 equals 0.0949 divided by 2, 0.047, 0.04745. Therefore, the mass of oxygen, we know moles is equal to mass of mR. Mass is equal to mass of O2 is equal to 0.04745 times by mR of oxygen, which is 32. And now we should get the mass. One 1.5184, 1.52. To 3 significant figures, or just 1.52. Question 2. A different mass of sulfur trioxide was heated, allowed to reach equilibrium at 1050 Kelvin. That's going to be key. We might need it later on. The amounts of each substance in the equilibrium mixture shown in table 4. Equilibrium moles for all of them. For this reaction at 1050 Kelvin, the equilibrium constant Kp is that. Calculate the mole fraction of each substance at equilibrium. Give the expression for the equilibrium constant. Calculate the total pressure in pascals of this equilibrium mixture. Now this, I'd say, is a harder question than those normal questions you get, where it's like a 6 marker, calculate value of Kp, and you have to find equilibrium moles, mole fraction, partial pressure, and then you find total pressure, and then you can find Kp. Because this one, it's got 3 different parts to it. It's not just like one question, it's got 3 different parts. First things first, we want to calculate the mole fraction of each substance at equilibrium. That's pretty easy. Mole fraction is just going to be, sulfur trioxide is just going to be 0.320 over the total thing. What is the total moles? Well, the total moles is going to be 0.320 plus 1.20 plus 0.600, which is 2.12. Therefore, so sulfur trioxide is going to be 0.320 over the total moles, 2.12, and we get 0.15. For sulfur dioxide, 1.20 over 2.12 0.57 0.57, and for O2 it's going to be 0.600 over 2.12, which is going to be 0.28. So now we've done the first step. We've calculated moles of each, mole fraction of each substance at equilibrium. A lot easier than I thought. I thought it would be a lot harder, but yeah, it's just going to be this over the total moles, which you just need a simple calculation: 0.320 plus 1.20 plus 0.600. Give the expression for the equilibrium constant Kp, just as given expression. So, well, Kp is going to be, remember with Kp, is curly brackets. With Kc, it's square brackets. We're dealing with Kp. I got confused on an equilibrium Kp question, and I lost like 1-2 marks just because I used square brackets instead of curly brackets. And it just remember Kp curly brackets. So Kp is going to be curly bracket products, which in this case is going to be, which one is going to be the products and which one is going to be the reactants? Well, think about it. We're going, yeah, because the sulfur trioxide is being heated, so the reactant's being heated to form the products. So the products is going to be partial pressure of SO2 squared times by of just O2. The reason we square it, the reason we square it is because there's 2 moles of it, over P SO3 squared. Same thing again, it's got 2 moles, therefore we square it. Now to actually calculate the total pressure in pascals of this equilibrium mixture. Well, let's think about it. Total pressure in pascals of this equilibrium mixture. Now what can we do here? Well, we know the total pressure so total pressure is equilibrium mixture. But we know Kp will give us will not give us the total pressure of the equilibrium mixture. What we're going to have to do is P is equal to move Kp into this equation. So how do we do that? Well, if we divide by Kp, we will get, actually what we'll get is, forget that, we'll get pure pressure of SO3 squared times by Kp over SO2 squared times by O2. All we've done, because it's divided, flipped it over and times by that. And now to find the pressure, we just substitute the values in. So what is it going to be? Well, it's going to be, well, we know it's at, yeah, we already know the KP is 7.6 times by 10 to the power of 5. So let's put the values in our calculator. 7.62 times by 10 to the power of 5 times by of SO3 squared. Well, what's SO3? 0.15. The more fractions over 0.57 squared times by 0.28, and we get 1.88 times by 10 to the power of 1, 2, 3, 4, 5 to the power of 5. 1.88 times by 10 to the power of 5 pascals. And there's a quick mistake here. I shouldn't have done P because it's actually not the P, the pressures, Bosch pressures. What this actually is the mole fraction. So you can just use anything really. Let's use lambda. So we use lambda instead. Get rid of P and use lambda instead. But a minor error. It's not a great error because we're still going to get the correct answer, but we'll probably might lose a mark because it's not actually the P of SO3 squared, the partial pressure of SO3 squared. It's lambda SO3 squared, the mole fraction. And then 7.3 says, for this reaction at 1050 Kelvin, the equilibrium constant Kp is that. For this reaction at 500 Kelvin, the equilibrium constant Kp is this. What can we notice between these two? Well, the Kp value has gotten smaller. Explain how this information can be used to deduce that a forward reaction is endothermic. Well, what can we see? What can we tell from these two values and the temperature values? Well, we know that Kp is higher at higher temperatures. Clearly see that when Kp is 7.6 times by 10 to the power 5 at 1050 Kelvin, 1050 Kelvin, and Kp is significantly smaller at 500 Kelvin. So Kp is higher at higher temperatures. Because at a higher temperature, equilibrium shifts to the right / forward direction, hence forward reaction is endothermic. And then 7.4, deduce the units of Kp. That's it for 2 marks. So use data from question 7.3 to calculate the value of Kp. Oh, we're trying to calculate the value of Kp as well. I just saw the deduce the units. So Kp, I'm going to do the whole of it just to show you guys. Curly brackets of SO2 times by O2 Oh, what can we notice from these reactions? We know it's at 500 Kelvin, and we know Kp at 500 Kelvin is 3.94 times by 10 to the power 4. Times by 10 to the power 4. So it's just going to be the square root of that. Square root of 3.94 times by 10 to the power 4. And we will get 198.5. 198.5. And now for the units, well, remember at the beginning of the question it's in pascals, so we're working with pascals, not kilopascals. So it's going to be pascals. What's going to be what? Products of reactants. So it's going to be PA. So by PA to power of a half, because that is the number of moles of oxygen, over PA, because it's just 1. And what you'll get is the PA's will cancel out, and now you're left with PA to the power of a half. So don't be like intimidated if you see like to the power of a half or to 1/3. It works the exact same way. You just raise the power when you're using it for Kp. So PA to the power of a half moles. That's the end of question 7.